Big Slick here with a video about fixing up an old RCA WO-33B CRT type tube type oscilloscope. This unit required a lot of work in order to perform reasonably well, so let me go through some of the steps that I did. First of all, I replaced all of the electrolytic capacitors. I normally do not do that anymore, but in this case all but one can was just completely bad, totally open. On the ESR meter here, I'll show you that this can, which was a 4-section 40-20-20-10 at 450 volts, this can was completely open. These two super dry cap electrolytics 4 mics at 450 volts, these were both completely open. The only can that was good was this one, and I actually think it possibly could have been a replacement based upon some soldering that was done in that area of the circuit. This one was still good, but considering I was replacing everything else, I went ahead and replaced this one too. So let me hook up this ESR meter onto these caps and I'll show you how bad these were. Okay, the main filter can that, like I say, was completely open. I'll show you here. I have this on, so right there is full continuity. So we'll test each section and you'll see you can't even get a reading on this. Each one of these just totally and completely open. Some of the worst capacitors I've seen in a while. You can't even get a reading on the ESR meter. So let me go over to the two small ones here. Here's this one. Nothing. Here is this other one. Nothing at all. So these were all completely open, and the only one that was any good was the large can. We'll hook that one up now. This one here could have been left in circuit. 1.8 ESR is a very low reading. 0.99, excellent. So this can could have been left, but it wasn't worth it considering that I had to get into there. The next thing I had to do, a lot of the carbon resistors had gone up in value, and most of these were 5% in the circuit. So there's a variety of new ones in here. See, 1, 2, 3, 4, 5, 6, just on this side of the board. On this side there was more. There's 4 new ones in this part of the circuit, 2 here, and that looks to be all there. There's some in the back too. Most of these, all of these capacitors were good. They were all Mylar and there was no problems with them. So from that standpoint, I didn't have to recap it except for electrolytics. On the back of the unit, you can see this is mainly the power supply area, the high voltage. New electrolytic capacitors, some new carbon resistors replaced. A few other upgrades that I did that I'll talk about later. In case you're fixing one of these up, the R11 control is the one right behind this area right here, looking from the back to the right of the CRT socket. This is the astigmatism control, and this one here is, it's like basically an AC balance. You could say it works for the tube heaters, but it's actually more complicated than that. It works actually, it highly affects the trace whenever you're testing very sensitive sine waves. So in order to get minimum distortion, you have to adjust this. But I'll go beyond that here in a little bit, because what I did is I converted this unit to use DC filaments on the four control tubes in here, obviously not the CRT tube. And the reason I did that is you could not get this unit to perform with reasonable low distortion without doing that. There was just far too much distortion in sine waves, and no amount of adjustment or tweaking the circuit or putting a humdinger in, I tried all of it, none of it works. This basically was a humdinger, but even using two fixed resistors, nothing worked except for converting to DC filaments, and that has been outstanding. For the DC filaments, I used an external power brick. It's actually a 12 volt 3 amp. There was no room to mount something inside, especially in order to keep the distortion down. So what I have here is a LM317 based regulator board, and I have the filaments adjusted to exactly 6.0 volts, and that pulls approximately 1.4 amps, which is pushing this LM317 pretty hard. It's rated for 1.5 amps. I've run it for 8 hours straight. I've had no problems with it, so I'm going to say it can handle it. I also have it heat sunk to the back of the chassis here. It was on its own little heat sink, but the heat sink itself is touching the chassis, and also have some thermal compound to help with the heat conductivity. So that's how I went ahead and converted this to DC filaments, and I have these hooked up right now that I can show you what the DC voltage is on the tubes. It settles right in at around 6.0 after maybe a minute or two of operation. 6.039 DC on the filaments of these tubes, so that's well within their operating range. You're always anything within 5 to 10% is always acceptable. So these will actually last a little longer. They're running a little cooler, and as I say, you know, you can feel this chassis on the side here where it's heat sunk, and it really only barely gets warm here. So I think this LM317 will handle this. If not, I can just simply buy a voltage regulator board that can handle more output current. It's not a big deal. It'll be easy to pop right in here. But I like this because it didn't take up much room, and I had it already on hand. Another change that I made to this unit, I removed the input variable capacitor, because in order to use modern probes which already have their variable capacitor built into them for the adjustment, you can't have it both places. So in order to use the modern probes, it was mounted right here, the first thing off of the input going to ground, and I just simply removed it. This was it right here. Now I'll just keep it around for another project if I need it. But if you're going to run modern probes with this old scope, you need to remove the adjustment capacitor that's right off of the input, and you will use you will calibrate the probe using the built-in capacitor built into the probe, just like you would on a more modern oscilloscope. Here I have a modern oscilloscope probe hooked up. It's a standard X1, X10 probe. We have it in the X1 position. It's on the highest gain sensitivity on the scope, and you can see the trace is nice and flat. There's very little to no ripple in that. This is on, there you can see it's nice and flat there. There's just nothing going on there in terms of an antique scope. And take this off of here. You can see how sensitive it is. very sensitive on the low end now. Before, the performance was terrible. So what I'm going to do is I'm going to feed in a very small sine wave. I'll feed it in at maybe 120 hertz or something like that, and I'll show you what it looks like on here. Okay, I'm feeding in the absolute lowest signal that I can from this low distortion function generator. It's 1.1 millivolts peak to peak, and when we go back to frequency here, it's 120 hertz, and I have this turned all the way down. This is the lowest signal it can feed, and you can see we already have a nice signal here on the scope, nice clean trace. That's the maximum amplification I can get on it, but like I say, that's actually as good or better as my lot more newer scope. So we'll turn this up a little higher here. A little more there. I'll turn it up even further. And as you can see, that is a nice clean trace. And in order to dial that in, what you have to do is this balance control that I was telling you about, it's located right in this area. That's accessible both from the front right there and from the back. You have to adjust that at these very low signal levels in order to get this trace as clean as possible. So it's working outstanding right now. On this high gain vertical range here, it's not wideband. So even if you feed in a 1 kilohertz square wave, it's not perfect. It's not bad though. Let me set that up. Okay, there's a 1 kilohertz square wave, and again we're still at the absolute maximum high gain sensitivity. And that looks pretty good actually. I can't complain about that much. If you adjust the sweep rate here, you can see we're dialing it in here. Now we have 3 going across the screen here. And there's 2. So as you can see, for the height that we're running at here, that's actually pretty clean. I'm kind of surprised. That's excellent. You can't ask for more than that from an old scope. So we'll go up into the other gain settings. Here's what they call high gain 0.15. There's a bit of tilt on this one, and this one doesn't have a separate adjustment in relation to the other two. You simply have to set it and it adjusts all 3. That's the best I can get on that one. On the 0.5 setting, I think it cleans up pretty well. A bit of tilt there, but there again, this is not a wide range at this position here, so there's definitely compromises on the low end on these old scopes. Now when you get up into wideband, it's very nice. So there's your 1.5. Go up to 5. Go up to 15. It's nice. And I can only feed 50 to a certain level. I can't drive the 150, it's just too much there for my signal generator. Okay, now we'll try to show you the maximum usable bandwidth. I believe the manual says that this goes up to 3 or 4 megahertz, right around in there. I'll show you what, in my opinion, it actually does. Okay, this is a 1 megahertz sine wave, as you see right there. And as you notice on these old scopes, the retrace blanking is not very effective. It somewhat has to do with the intensity, but still it's going to be there. And so you could see a 1 megahertz signal pretty good, and it's actually pretty clean if you actually look at the primary sine wave. Now once you get beyond this, it starts getting a little dubious as to how useful it is, although you can still see that a signal is there. So I suppose that is usable, but it gets to a point where it's difficult to figure out how clean the signal is. You're simply going to be able to notice that the signal's there. And that is useful a lot of times. So we'll set this up to 2 megahertz. Okay, that's 2 megahertz, and you see that it's still dialed in pretty well there, and you can still see that it's there, and it really isn't even dropping off in amplitude yet either. Okay, now we're up to 3 megahertz, and as you see, we're having trouble dialing it in here. It's going to be very, very touchy at this. You can sort of, can't really get it stable there, but it's trying. We'll try to back it off further, see if we can find a stable spot. There, that's as stable as it can get, and I mean it's acceptable. You can still see a reasonably clean sine wave, although this is obviously a huge compromise at this level. So 3 megahertz there again is usable, at least to see that there's a signal there. Now we'll show some of the other features that this scope has. It has the quick trace, which is a octopus style curve tracer, and on this you use the ground input and this input over here, which I changed to a standard banana jack because the built-in RCA was just simply not practical or compatible with any type of probe leads that I have. So with this you can use a standard multimeter lead, or you can use standard banana pinch leads. So I'll hook something up here and we'll go from there. Whenever you put this in quick trace mode, you have to also, it's easy to forget, you have to flick this quick trace up here from scope normal. That is one usability thing here that was less than ideal in my opinion. It would have been a lot nicer if this would have automatically switched this on one of these two positions whenever you put it into quick trace. So you have to remember to do it. When you go back to using the scope, you have to remember to put it back down in, because it's odd, the scope will still read, but there's like some subtle differences depending on where the positioning is, how accurate and how clean it is if you forget and you leave it in this quick trace setting. But in any event, we're using quick trace now, so let me grab some probes and I'll be back. Okay, here's a JFET. We'll test this first. As you see, it's testing good 3 is the gate. So let me show you this one here. Okay, here we are testing this. This is a 2N5457, and that's a sample pattern that you get. We'll test the other one, the other side of it right here. And so now we're connecting pins 1 and 3. Before it was pins 2 and 3. So as you see, you get a similar one. Now when you connect 1 and 2, okay, connecting 1 and 2, you'll see kind of an odd looking pattern on there, but you still do have the step pattern as you see. Now let me show you a bad JFET, which actually I was sorting through these the other day, and it turns out that I have one new one that's bad. Okay, to show you this one here, this one simply tests as 2 diodes. And this is the same model of JFET. If you connect the source and the drain here, you could see it's basically shorted. You're getting a straight line, and that's what you would see if you simply connected these two test leads together. And that's what's defective on this. So you could have used this instead of a device like this to spot this defect. Okay, this is a standard 1N model 407 diode, just it's typical L shape. Okay, here's this typical driver transistor. It's an MJE 15031. We'll connect that up. Okay, there it is, connected to pins 1 and 2. There's pins 2 and 3. And pins 1 and 3. In case you're curious, this is a 42 volt supply that's feeding this. So it is a higher voltage than a lot of curve tracers. Now I have another unit that is a good old-fashioned octopus, and it has a switchable 5 volt and 50 volt, but this one is 42. Now I'm wondering whether you might have to be a little bit cautious on testing like small signal preamp transistors. Possibly. I think a quick test probably wouldn't hurt them. In my experiments with it, I haven't seen a problem, but you know, whether it's degrading, I suppose I would personally not have any other way of knowing other than looking at the curve itself, which usually when these things are defective, you will see a slant someplace or other type of distortion. You won't see the clean breaks like this, either horizontal or vertical. You'll see ones that shoot off at angles, and that tends to show that you have internal breakdown. Okay, you can test capacitors, at least lower value capacitors on here, and 4 microfarad would be within the range that you can test. And as you see, all you do is tilt the line a little bit, and this is totally wrong behavior for a capacitor. And this is another way you could have spotted this defective in circuit. Obviously power off and capacitor discharged. And as you'll see, that is a completely bogus reading. It's very bad capacitor. We'll check a few of these other ones. Okay, here's the other dry electrolytic, and as you'll see, it has a little bit of an oval pattern, and this is, you should see an oval pattern, but you can see that this one is obviously bad. Let me go ahead and get a good 4 microfarad as a comparison, and I'll show you that. Okay, this is a brand new, I believe it's a, I want to say it's a Panasonic or a Nichicon, I forget which. But this is a 4.7, and as you see, you get a pretty nice circle there, and that's what a 4.7 is going to look like on here. So you could see how bad those other two capacitors were. One was dead as a doornail, the other one was virtually dead. Let's try that other can electrolytic that looked like it was completely open and see what it does. Okay, here's one section of this can. As you see, it's dead as a doornail. Let's try the other section. Again, completely dead. This section completely dead. And that section completely dead. This is the worst capacitor that I've seen for a while. I mean, it is just completely open. Okay, this is a 5-volt Zener diode. It's an example of testing that. This is an example of a curved trace of a Schottky diode. Here is an amber LED, which, as you see, the LED is lighting up also. And this is a 1000 ohm resistor. As you see, it just becomes a slanted line. You can only test resistance to a limited degree on an octopus. Okay, this is a 10,000 ohm resistor, and as you see, we're starting to approach horizontal again, and once you get to horizontal, you can no longer read resistance because to the octopus it just tests open. Here's a 22,000 ohm resistor, and we're even closer to being horizontal, so we're starting to reach the end of where this will test. Here's an example of the transformer ring test. As you see, this is a Thordarson new old stock power transformer. I'm testing it across the primary. I think this test is only going to be useful in some instances. Here's how it changes. I'll show here. Shorting these two together, you'll see the waveform gets distorted. But my own testing on this is that it's kind of inconsistent, so I think it would only be useful in some situations, in some types of transformers. Doesn't seem to work on chokes at all as far as I can tell. And here's a picture of the unit back in the case and cleaned up. This one was in really nice shape. There's hardly a mark on it anywhere. Just very, very minor. Okay, thanks for watching. Bye.